I am Octavio Alberto Agustin Aquino, and this is the talk associated with the paper An Algebraic Symmetric Analysis of Counterpoint and Modulation in the Music of Claudio Monteverdi. This is joint work with my student and co-author Brandon Jaime Curiel Lopez, and it grew out of his bachelor thesis in applied mathematics at Universidad Tecnológica de la Mixteca. Claudio Monteverdi stands at one of the decisive turning points in Western music. He belongs to the wall of Renaissance counterpoint, but he also opens the door to the Baroque, to opera, to dramatic harmony, and to a freer use of dissonance in the service of expression. This transition was not peaceful. Around 1600, theorists and composers were debating the relation between musical principles and expressive means. The older style, later called the prima pratica, treated counterpoint and harmony as governing principles. The newer style, Monteverdi's seconda pratica, reversed the priority. The text, the dramatic situation, and the emotional force of the words could command the harmony. The most famous critic of Monteverdi was Giovanni Artusi. To Artusi, some of Monteverdi's progressions were below his alleged skills. In particular, he objected to harmonic motions in the madrigal O Mirtillo, hearing them as errors rather than innovations. But it raises a mathematical and musicological question. Were these passages truly or merely arbitrary rule-breaking, or is there another kind of rationale behind them? The purpose of this work is to show that Monteverdi's innovations can be studied through algebraic symmetry. The point is not to claim that Monteverdi consciously calculated in modular arithmetic, even if there is evidence that by his time equal temperament was already a reasonable approximation. Rather, the claim is that Mazzola's mathematical theory of counterpoint and modulation give us a precise language for describing the structural logic of what Monteverdi does. Let us illustrate algebraic symmetries with the following example. First, consider the 12 pitch classes represented by the integers modulo 12, set 12. In this setting, an interval is also an element of set 12. We divide the 12 intervals into consonances and dissonances. For traditional counterpoint, the consonant intervals are k equals 0, 3, 4, 7, 8, 9. These are the unison or octave, the minor and major thirds, the fifth, and the minor and major sixths. The complementary set D equals 1, 2, 5, 6, 10, 11 consists of the dissonances. What makes this division mathematically special is that this is not just a list. It is a strong dichotomy, meaning that there exists a unique affine transformation that exchanges consonance and dissonance, namely px equals 5x plus 2 modulo 12. This map is called the polarity of the dichotomy. Thus, the elementary distinction between consonance and dissonance has a hidden symmetry. This is the starting point of Mazzola's model. As Klaus-Jürgen Sachs emphasizes, counterpoint is not only a matter of one melody against another, but also about one interval against another. To model this, we use dual numbers over set 12. A contrapuntal interval is written as x plus epsilon y. Here x is the pitch of the cantus firmus and y is the interval of the discanthus above it. Now comes the key idea. For a given consonance, not every possible next consonance is equally natural, since some sort of tension is to be induced and resolved. Mazzola's theory selects preferred successors using affine symmetries of the dual number space. These symmetries transform the consonant-dissonance division and must satisfy three conditions for a given consonant counterpoint interval. The present consonance must be a deformed dissonance. The polarity structure must be preserved, meaning that the original polarity has to be a polarity of the deformed dichotomy as well. And the overlap between transformed consonances and ordinary consonances must be maximal. This intersection is precisely the set of admitted successors. Musically, this gives a model of contrapuntal preference. Mathematically, it gives a way of counting and comparing transformations within a natural subgroup of symmetries. Some transitions require many symmetries. Others are parsimonious. They are mediated by a single symmetry. This notion of parsimony will be crucial in reading Monteverdi. Let us look at the kind of phenomenon we want to explain. In several passages discussed by Jo Jung-Kang, Monteverdi uses progression from a fifth to a third. These 5-3 successions are valid in Mazzola's model and also compatible with traditional rules in important respects. But in our analysis, their special feature is that each such transition is mediated by a single counterpoint symmetry. Even more strikingly, a symmetry that fixes the cantus firmus appears at expressive words or situations. In Confitebor primo, it marks mirabilium, wonders. In Ma tu più che mai dura, it emphasizes pietà, compassion. In Io mi son giovinetta, it coincides with leaving the chromatic E sharp on fuggi, flee, a note that literally flees from the key signature. This suggests that Monteverdi is not merely avoiding forbidden parallels or adding local color. He's using a structural parsimonious transformation at words of emotional or theological significance. The symmetry is not an ornament added by the analyst, it reflects a recurring musical behavior. Other passages behave differently. In 8-6 progression, for example, where an octave moves to a sixth, the transitions tend to require more symmetries. These are less parsimonious, and they often occur in richer textures, especially when more voices enter. Thus, the algebraic model distinguishes between two kinds of musical event: a focused expressive transformation mediated by one symmetry, and a denser contrapuntal texture mediated by several simultaneous symmetries. So far, we have discussed local counterpoint, how an interval moves to the next, but Monteverdi's innovation also concerned larger scale harmonic motion. For this, we turn to Mazzola's quantum model of modulation. First, we have to understand that the tonality stemming from a major scale is the set of chords built by stacking diatonic thirds. This can be seen as a topological space, namely the nerve of the system of sets, where each chord is a zero simplex, a pair of chords that share a common tone is a one simplex, this is Schoenberg's harmonious band, and three chords that share a common tone form a two simplex. This is homeomorphic to a Möbius band. Once tonality is understood through the triadic interpretation, it turns out that there are exactly 5 minimal cadential sets, or cadences. This can be seen as signatures. Their appearance allows us to infer which tonality we are hearing. A modulation is a passage from one tonality to another as described by Arnold Schoenberg. In the model, a modulation is controlled by an affine symmetry called a modulator. The model then asks for a minimal set called a modulation quantum, which remains invariant under the modulator and contains enough information to identify the target tonality through its pivot thirds and then confirming it by displaying a cadence. This is a mathematical way of saying that a modulation is not merely a change of key. It has a minimal structural carrier, a small collection of tones or chords that make the transition intelligible and effective. Our modulation analysis focuses on l'Orfeo, where harmony serves dramatic narrative. This is especially appropriate because opera is precisely the genre in which Monteverdi's Seconda Pratica finds one of its most powerful expressions. In l'Orfeo, tonal regions are not neutral, they are associated with dramatic states. The succession of keys can narrate Orpheus' emotional journey. The first aria of the first act, In questo lieto e fortunato giorno, already offers a miniature of the opera's dramatic tonal structure. The fields of phrase are represented by C major. D major is associated with Euridice. A major evokes the sphere of the underworld, and the return to C major restores the opening world of phrase. Another important case discussed by Haley Perrett is the movement between major and minor. The relative transformation explains how a cadence of the fourth and fifth degrees for the major mode is transformed into the cadence of the second and third degrees for the minor mode. The passage uses for not just a color change, it has a structural mechanism, and that mechanism corresponds to the dramatic ambiguity of the text. In the arietta Ecco pur, the music moves between G minor and its relative major, B flat, and back again. In the arietta Mira de Mira Orfeo, the modulation creates a contrast and anticipates the sudden entrance of La Messaggera with the doleful news of Euridice's death. The result is poignant. The music can speak of return, sunlight, or joy, while already carrying the shadow of loss. This is exactly the expressive power of the Seconda Pratica. Harmony follows the blood, but it does so structured, not chaos. This also gives an answer to Artusi. Artusi heard certain Monteverdian passages as errors against the inherited rules. From the perspective of this analysis, however, Monteverdi's procedure is not a rejection of logic. It is an expansion of logic. The old rules are not quite destroyed. They are transformed so that dissonance, modulation, and contrapuntal freedom can serve the expressive demands of the text. There is a broader methodological point here. Mathematics does not replace historical listening. It does not tell us what Monteverdi must have meant, but it can reveal patterns that are difficult to see otherwise. It can distinguish arbitrary exception from systematic behavior. It can show when a musical gesture is isolated and when it belongs to a family of transformation. In this sense, algebraic symmetry becomes a tool for musicology. It gives precision to the intuition that Monteverdi's innovations were disciplined, not careless, expressive, but not arbitrary. The central claim of this work is therefore simple. Monteverdi's contrapuntal and harmonic language contains a hidden mathematical coherence. In local counterpoint, this coherence appears through admitted successors and parsimonious symmetries. In larger scale harmonic motion, it appears through quantized modulation and relative transformation between tonal regions. Together, these models show that the seconda pratica was not merely a loosening of rules. It was the emergence of a richer musical grammar, one capable of absorbing dissonance, chromaticism, and modulation into a dramatic logic. So the question is not whether Monteverdi broke the rules. Of course, he challenged inherited rules. The deeper question is what kind of order replaced them. Our answer is an order of symmetry, transformation, and expressive structure. Thank you very much.